Hey guys, so let's get ready. Today I'll tell you all you need to know about the gradient boosting, the key machine learning algorithm for tabular data. Uh, by tabular, I mean data stored in tables. Gradient boosting is one of the best leading algorithms for predictions on tables, such as, for example, prices, loan defaults, the algorithm extensively used in banking. And moreover, it is a gateway algorithm to start with machine learning. All you need to know is 1+ year of coding experience. You should be able to understand some basic Python, and I will cover some library issues in Python. And today we will understand how the algorithm actually works, how the gradient boosting algorithm works. We will understand it through code. There will be almost no math, no formulas, only the code, which we all hopefully like as a medium to explain some complex topic. Today we will implement the algorithm of gradient boosting in plain Python up to the tiniest logical component, every formula, everything. So let me just share my screen. You should be able to see it. I hope it's clear. So here's a preview of what we will be doing today. Here's some libraries imported. Here's a Numpy library, Python array manipulation library. Here's sklearn. Sklearn is one of the leading machine learning libraries in Python. However, we will be using it only to compare the performance of our implementation to something. So to understand whether we implemented the algorithm correctly, we compare the performance of our algorithm with sklearn. Sklearn is golden standard machine learning library in Python. So we will implement the gradient boosting algorithm. However, one of the key parts of the algorithm is decision tree. Gradient boosting is basically training lots of decision trees. And to understand the gradient boosting, you need to also understand decision tree. It was a preview of what we will implement together. The full code, you will be able to view it after the talk ends. And we will gradually build up to this complex code step by step. So first of all, what is it? What is opened? Probably if you're not familiar with data science toolbox, it's a notebook. It's basically a Python command line which lets you manipulate data, run some calculations. So it's just a Python console split in cells. It is very convenient for data science because you can gradually improve your understanding of the data with each cell. So back to the topic, Numpy library, Python array manipulation library. We will import it as NP, a common alias for this library. We will need it to manipulate arrays. It's one of the only, it's probably the only library which our implementation needs because Python lacks convenient array functionality by default. So first of all, let's create a one-dimensional array. To do this, we just pass a Python list with numbers to np.array. Here's our one-dimensional array. We can also create a two-dimensional array with NumPy. It's basically we are passing a list of lists to np.array, and it interprets each sublist as a row. Here's how you can create a two-dimensional array in Numpy. By the way, when I call them one-dimensional, two-dimensional arrays, I mean that it has only one dimension. For example, it's only a row of data, and this array have two dimensions. It's more like a matrix, a table. Probably the closest analogy would be a table. However, it is really used to multiplicate matrices, but what do I know? So you can also use Numpy to apply some mathematical functions to all elements in array, some aggregate functions. For example, you can calculate average value in an array by using np.mean, meaning average value. You can also apply functions while not aggregating all values in an array, but instead applying the function to each individual element. For example, with np.power, you can square, as a result, you can square each element in the array. So that's why I call them one-dimensional and two-dimensional. Here's a method .shape, which lets us see the dimensions of array. Basically, here's our array, two-dimensional array. It has a shape of 3 on 3, and one-dimensional array is has only one shape, as you can see. Only one shape, that's why it's called one-dimensional. Probably very important to grasp the concept of array slices in Numpy. Here's our two-dimensional arrays, and here's how we can choose only the first row, zero-based indexing, and the first argument to these square brackets lets us specify a certain row, and the second argument after the comma lets us choose the columns. But two dots just mean all the elements in this row. We are taking all the elements in this row. The same with columns. Here's how we can select the first column of an array. As you can see, it's just our first column. And we can also select a single element like this. Here's we selecting the element in the position of 0 by first dimension and 0 by second dimension. And here's we selecting the element in first row using zero-based indexing and zeros column. So I hope it's getting a little bit clearer how we can manipulate elements in Numpy. Here's a couple more functions. For example, np.zeros lets you create two-dimensional arrays, one-dimensional arrays. Here's how can I create two-dimensional array. We can also create a dimensional array with only a single element. In this case, just 0. We're gonna use this functionality later. It seems pointless probably at this point, but we will need the Numpy functions which just create arrays with just one element. And we can also use Boolean series. For example, here's how can we analyze each element in array by some Boolean condition. For example, here we take the zeros row of our two-dimensional array, and we calculate the remainder from the division by 2 and see that it is equal to 0. So 1 divided by 2, the remainder is 1, so the output is false. The second element, 2, divided by 2, the remainder is 0, so the output is true. So we apply some logical function to a slice of our two-dimensional array. And we can filter the elements in our two-dimensional array using this Boolean series. So we apply, first let's have a look at the data. Remember slices. We take the first row, the zeros row, to be precise, and we apply this Boolean series to our array. Here's what we get. We get subarray, which outputs only the second element, because only that element matches our condition. And we can also invert this condition. It is a common Python operator to invert the condition. It works like this. So when we are not inverting our condition, we get the second element, and we're inverting this, we get the others, which doesn't match our condition. So it's always Numpy. Getting back to machine learning, here's we will use sklearn library. It's basically a library for machine learning, but it has some peculiar functionality. It has toy datasets. Toy datasets meaning some data, tables with data, machine learning model for strictly this purpose, some convenient datasets to benchmark our machine learning models. It's just perfect for this purpose. We will be analyzing Boston house prices dataset. It looks like this. With load Boston, we just load the data. It's an array of features in machine learning. Probably a quick disclaimer, machine learning is something which outputs historical, which inputs historical records upon some numerical measure. For example, house prices, Boston house prices. Here's one row of this data is all the characteristics of a certain house measured. And we will try to predict the price using these historical measures. So we don't need to understand what each particular measurement means. We only need to understand that all the columns, we have 13 columns in this array and 506 observations. We only need to understand that it is all one column of something measured for this house. If you're interested, here's their names, but they're irrelevant for us. It's a pre-collected dataset. They are correct. The dataset is okay. It is specifically for testing purpose, for us not to think too much about it. So we're loaded the features array, and we load the prices array. It's basically the price of each individual house. So for example, here's measurements of the first of our 506 houses, and here's its price. The order is there in corresponding order. You may think that these are rather cheap houses, but probably measurements were far in the past. Let's not dive into how it corresponds to reality yet. Here's another concept from machine learning. We're gonna use sklearn for that. It's fine because it's very simple. We don't need to implement this functionality. We're going to split all of this data set into two parts, into the training part and into the testing part. In the training, we will have 379 observations and all the same features. And in the testing part, we are going to have 127 observations. The splitting is totally random. Why do we need it? We need it to train, basically, that's why it's called X train, Y train. By the way, X is the name for a features array, Y for prices or target array. It is a common machine learning terminology. Why do we need to split the data into two parts? Because it would be incorrect to assess the quality of our machine learning models on the same data set as we've trained it upon. Because if the model already seen these values, it's gonna be able to predict the values for such data with 100% accuracy. However, in the real world, the model haven't seen the data, and it needs to approximate on new information. The model needs to perform good on new information. It's all for our data set. We will gonna be testing our models on this data set. So a little bit more theory. So that's how it looks, just to finish the understanding. Here's how decision tree algorithm works. We're going to be implementing a decision tree before we move to gradient boosting. Actually, the gradient boosting is the easiest part. The trickiest part is to understand how the decision tree actually works. We're going to cover the gradient boosting, don't worry. We are just focused on understanding the fundamentals for now. We provide for decision tree, or basically any other algorithm works like this. Here's the decision tree, but you can switch it to gradient boosting. It works the same. It trains on examples of past observations with target values, in this case, prices. And it is used to predict prices or target value for new observations with all the same measurements, but without prices. It works like this. We provide houses with prices and houses without prices for which we need prediction. And the model predicts the price based on the best of its understanding of the logic in past observations. A trained decision tree works like this. It basically asks about the data. So, for example, the first question is whether the size of the house is less than or equal to 200. The answer is no. So we proceed to this branch. And then we ask the second question about the rooms in this case. Noted that questions are different based on the first question. And based upon our answers, model makes prediction 300 right here. So that's what we are going to be implementing, dramatically simplified. Let's outline the structure using code. Here's our class object, decision tree regressor from scratch, because we're implementing it from scratch. What methods do we need in the first iteration? Let's just define an empty structure. The fit method in machine learning is commonly called the training method. The method for training our machine learning models is called using the fit word because the model is fitting to the data. Probably some shady terminology for you at the moment, but it is okay. Let's call it this way. It's called this way in all the libraries, and we will obviously need the predict method. So we're not doing anything yet when we're fitting to our data. Notice the arguments x and y, our features array, and our target array. And we will predict with ones. We'll just predict the price of one based on the number of observations and x. So basically, we've got data for 100 houses. We see that it's 100 by using a shape 0, and we predict with ones for each observation. It's a really bad model, obviously, but we're just outlining the underlying structure. So we initialize our decision tree. We're fitting it to the data, though we know that nothing happens. It's okay. And then we are predicting for X test. Remember that we are splitted our data sets, to two parts, training and testing. And please don't focus too much on the visualization library. It's a common library for data visualization. I use it only to plot two charts against each other and label the axis. This code basically renders this picture. So we've just predicted for our testing dataset. Let's see how it looks. Oh, sorry. It was a spoiler. I was not supposed to launch. It looks very bad. Here's our X test, Y test. Here's our true price. And here's our Y pred. It's what our really bad model just predicted. Obviously, it is a very bad model. We're going to be improving it soon. X-axis on this chart is just the number of observation. On this chart, you can notice that it is close to 120 observations, and in testing data set, we've got 127 observations. So it's just a comparison of what what our model predicts for the observation and what is the true value. So perfectly, it must be closer. Two lines must be closer. Our goal is to make these two lines closer to each other. We must have some numerical estimation of how bad our model is. We understand that it's bad using data visualization, but we must have some numerical criteria to assess it. We will be using MSE, mean squared error, to assess the quality, the performance of our machine learning models. It works like this. Here's our numpy.power function, which squares the result. We will be needing it here, and the mean function. So basically, we calculate the difference between our y true and y pred. We square the difference. Probably I should introduce some live elements into this. So, oh, sorry, haven't defined it. life elements are like this. So basically difference between the model, it's pretty huge, pretty much price -1, because our y-pred is just once. And we square the result. Why do we need it? Because some predictions may deviate in the minus and some in the plus. So y-pred may be higher, may be lower, and we need to treat each difference equally. And then we just find the average value of this difference, and we get the same number as by applying this function. We get 486, pretty much huge mean squared error. We want to decrease it. How do we decrease it? Let's try predicting with average value. So average value of y-test is probably close to 20, and this model is much better than just predicting with ones. So predicting with average value is not that bad. This method fit does something in comparison to the previous one. It calculates the average value in the training dataset, the average price in the training dataset. And then numpy.repeat means that we just, when it comes to predicting for new houses, we just output the mean value for the number of observations in the validation dataset. So let's initialize it, and as you can see, it's far better. We've had the MSE of 486, and just by predicting with mean value of the price, we've dramatically decreased the mean squared error. And here's how it looks on the chart. We're just predicting with something closer. It's already a little bit closer to the truth, not that close, but already better. How do we make it even better? So I'm not waiting for your answer here because it's not that trivial. Look at the data here. On the x-axis, here's the values of our 9th feature. So probably something like this feature of the training dataset and testing dataset, 9th feature of our data for every houses, plotted on a chart against the of the house. So it's just x-axis, x-train 9th feature, and the price. Notice that after a certain value of our 9th feature, we have a different distribution of the price. For example, for this cluster of observations, there are values which are less than 10, and they tend to be lower. They're concentrated on the lowest end, while before this 9th feature, whatever it may be, the values tend to be higher. So let's try splitting our data using this red line, this splitting condition, into 2 parts, and predicting with the average value of the price for this cluster as a result of splitting our data, and this cluster. Here's how it looks, still pretty simple. We just split the data using our condition, the Boolean series. As you probably remember, we can apply Boolean series to arrays of data to sort our elements into 2 parts. So the first, we just, this code does the following. it just remembers the two average values for this cluster and for this cluster. It's reflected here, pretty much simple code, which splits the data into two parts and remembers and stores two average values of the price. And then it predicts based on the value of now a ninth feature. So we calculate the number of observation in our validation testing dataset. Then we iterate over every observation in a dataset. We ask a question for every observation and a particular ninth feature, whether it is more than 500 or not, and predict based on the mean values. Notice that here's an if statement that outputs prediction to the result variable based on applying the condition to ninth feature of our observation. And then when the iteration is completed, it just outputs result. So it looks like this. We have two values of the mean, and we predict based on the feature, and the model approximates a little bit better. So for example, here is a high value, and this value is a little bit closer than that value. So taking into account information about this feature lets us be closer to the real values in y-tests. And our MSE is far better. Look at the previous value, 72. We've decreased it to 58. Not so dramatic as the previous decrease. I remind you, it's error, so the lower the error, the better. So this value, as you remember, basically measures the degree to which we perform bad, to which we measure incorrectly. So if we compare mean squared error of y-test to y-test, it's basically 0. Because we do not make mistakes if we assess two y-test lines, they are basically matched. We are trying to get the thing as close to 0 as possible, I remind you. Here's a little bit of complexity. Don't worry. Here's what I suggest to do. I suggest we split the data using the MSE. We want our MSE to drop as dramatically as possible. So why don't we look at all of the features? Why we only look at ninth feature of the X-train? Why don't we look at all features of the data set and choose the best splitting condition based on the drop in MSE? We can apply it on the training data set. Here's how we'll do it. Line by line. Obviously, to apply this criteria of MSE, we will need to use the MSE function inside the class. So we define it, it's the same MSE, some Python object-oriented stuff, but overall it's the same MSE. First of all, we want to iterate over all features in the data set and measure their MSE. We must store and update the minimum MSE variable, minimum MSE value in a variable to compare. For example, we've seen one feature and we want to compare to the second one. To do this, we want to store the MSE. On the next iteration, we want to compare the next MSE with the minimum one in order to know if the new features value is the minimum. So we need to store the MSE. By the way, feel free to read the code. Probably it's, if you know how to code well, it's probably more descriptive. It's pretty readable and it has comments. However, I have to go line by line for those of us struggling to understand the code. So we are storing the minimum MSE in order to compare it, in order to find the best minimum MSE in the array. We need to store the minimum value and update it as we go through the features. And we are storing the best feature, best value, because we want to find them among all the features. What's a feature for us is just a number. Here's it's our 9th feature. We reference it like that. And because of that, we just iterate over the number of columns. X.shape0 is the number of rows, and x.shape1 is the number of columns. So we iterate over the number of columns. And then we take all the values, really all the values in this column, and we see how this splitting condition applies. First of all, we initialize the Boolean series. For example, for x, we have some value of the feature. For example, let's apply it to this table. For example, we have a size of 100. We apply the condition and we split the data into two parts. Those houses with size less than 100, it's only one house in this case, and the other ones. We split the data like this on every iteration. Then we go to the next value of 200, and we split these houses, the first two houses, and the third and the fourth, because they are more than 200. And we go next in the same manner. We proceed in the same manner to split our data set based on this condition. Here's the splitting part. We've got a Boolean series applying this condition, splitting condition, and we've got two parts of x's and two parts of y's, y1, y2. So we've applied Boolean series. We've got 4 variables storing features, 2 parts of features and 2 parts of targets. For, in this case, prices. We are ready to calculate MSE for these 2 parts. What would happen if we predicted for this part using the average value? We calculate MSE for one of the parts using the average value on this part. So as you can see here, it is a pretty good idea to predict for this part using the average value of the price, and for this part using another average value. So we assess what would happen if we predict for both of these clusters using their average values. And then we use these 2 MSEs to combine them to assess the quality of the splitting condition, whether this splitting condition truly helps us to divide the data into 2 parts efficiently. To do this, we calculate the weighted MSE for a split. What is a weight? It's basically a share of the split. It's assessing how much observations in total gets into the one split. We multiply the first value of MSE for the first split to its share in the total. So whether it's, for example, one observation out of how much are in our training data set. Let me remember. 379. So we see if it's 1 divided by 379, or for the second part, if it's 378 divided by 379. Maybe a typo somewhere. So here's the weights for MSCs, and we calculate the weighted MSC like that. We need weights because it is fine if we are able to predict for the majority of the observations with small error. If we predict bad for this one observation, for example. So these errors are not born equal. They are requested in the proportion to the observations on which they are calculated. And we find the best MSC among all features. We update our minimum MSC if it's none. If it's not been initialized yet, every MSC is minimum MSC, it's best. And then we update after the first iteration is completed and minimum MSC has been initialized. We update the minimum MSC only if it's more than weighted MSC. If weighted MSC is less than minimum MSC, then it's not anymore a minimum MSC. We need to update it. And we need to update our best feature and best value as well. So when we've iterated over all combinations of features and values in the dataset and found minimum MSC, and what is more important, our best feature and best value, we are ready to do what we've done in the previous iteration of our decision tree. We are ready to apply the final condition. We are ready to just apply to the best feature condition with the best value. And we calculate the mean values for both of these parts by applying this Boolean series. It's okay that we apply a Boolean series calculated on the x to the y because we've take one column of the x, one feature, and we compare it against a condition. And then we apply this Boolean series to y array. They have the same shapes after that. So there is the same number of observations in x and y. That way, if we take only one column of x, there is the same number of observations as in y. So it is okay. And we found the best feature, the best splitting condition, and we just remember the average values in clusters that look like this, but probably the algorithm found something better than I did visually. The algorithm just remembers two values of y. And it predicts using these values like this. It applies the condition, but the values are not hard-coded. It's just our best feature and best value. The only difference between the previous iteration and that one is that this condition is not predefined in the code, but rather inferred through the training, through the fitting method. So you can see that our MSC is a little bit better. We've had 58 and now we've got 42. And here's how it looks. So it is a better splitting condition, and you can see it visually. It better reacts to peaks. I don't know, whatever it may be. It splits the data better. It is able to capture, for example, this peak. It's pretty close. It's a little bit closer than in this feature. This feature is better. So the only difference we need to complete our decision tree implementation is to do this recursively. So the real decision trees, as you remember, they do not ask one question of data. They ask multiple questions recursively. So how does it work? I need to introduce a data structure. Here's a Python dictionary, basically a hash table where there are keys and values. We will need to label every node in the tree. By the way, this thing's called nodes. We need to label them with zeros and ones in order for our implementation of decision tree to work. So the first node just got 0, and then based on the answer, it's 0, 0 or 0, 1. Here's how it looks in practice. Our decision tree, our built decision tree will look like this. Here's the first node and the condition. The first value in this tuple is the condition on which we're gonna split the data, and the second value in this tuple is the value on which we're gonna split. So what it means is that the first question we're gonna ask of the data when making predictions. Here's how a small trained decision tree looks. I explain it only to set a data structure which we'll be using to store the trained tree. So the first question we're going to ask of data is whether its fifth feature is less than or equal to 6.939. And then, based on the answer, if the answer is yes, we proceed to this node and we ask a question again. And if the answer is yes again, we proceed to this node. And then we output the value. I artificially restricted the depth of the tree to better resemble this structure. It has a depth of 2. Actual decision trees are deeper. So let's get to our implementation. It is a recursive fitting function. We're gonna record the argument to this function. Every time we call it, we incrementally increase the tree path. So first time we call it, it's 0. And the next time it's got some more values, whether 0 or 1. In recursive functions, we need a splitting, not splitting condition, stopping condition for recursive functions. So for us, the stopping condition would be if the maximum depth of the tree is reached. We need to be able to set the maximum depth of the tree. And we are gonna stop if there are no more observations to split. So if there is only one observation in X, if we split it the end of the data, then we will not proceed. So it's all with the stopping condition. We will also gonna be remembering our minimum MSE, our best split. I remind you that you're gonna be able to view this code, play with it. I will share the notebook at the end of the talk in the comment section, and you will be able to play with it. So getting next, we iterate all the same. I've tweaked the performance a little bit to make it more efficient, but it doesn't matter. All of this is the same. We've already discussed it. We're just iterating over the features and values. All of the combination of splitting conditions, split our values in two parts, calculate MSEs, and choose with the highest MSE drop. With the last MSE, probably it's better to say that this way. Then we will do the following. We apply our splitting condition to the data to get the best split again to reproduce. We've already did it, but we've lost it because we need to look at all pairs, and we apply it and we get the best split of the data. And then we record this information about the best split into our tree object for our path. So our path is 0. Let's discuss the first iteration. Our path is 0, 0 node, like this. And we want this splitting condition, tuple, in the form of tuple, to be stored as the value for this node. So the function does just that. And then the trickiest moment, it recursively calls itself 2 times with both parts of the data. It sounds scary, but we're doing just that. We're splitting the data recursively. We've got 400, close to 400 observations here, 200 here, 200 here, 100 here, 100 here. Obviously, values are not like that, but just to capture the principle that we're just splitting the data recursively, making it smaller, and predicting with better precision. It is a fact that the closer we are to the data, the better we are able to capture the price using the average value, to predict the price using average value, as shown by MSE. So this recursive calls, as they increase the value in this structure, they output the values for different nodes at each consecutive iteration, while simultaneously increasing our tree path. Our tree path looks like this, and we've got 2 answers to our question, 0 and 1, whether the condition is met and x1, y1 is going to the next iteration, and whether the condition, I switched them, whether the condition is not done, and whether it is done, and whether we proceed with the second part of the data. And we predict by traversing this tree. Here's a pretty complex part of the code. You can look at it later. I think I left it. I'll leave it as an exercise to the audience. Basically, just it goes over the tree path until it encounters a value that is not tuple. Notice that if we need to split the data further, the value is tuple. If we're not gonna need to split the data further, we've got a prediction value. So in this part, it reacts to the result being tuple, and it stops the traversing of the tree and outputs the result, the prediction, if it's not tuple. And it continues to split and increase the tree path if it's not tuple. So it looks like this. We recursively fit to the data, which makes our error even lower. As you can see, the previous error was 45. and we decreased it to 18. And we were able to fit closer to the data. Look at the previous example. We're just predicting with 2 values. And there are lots and lots of values with which to predict based on the data. And the error is far lower. So to the gradient boosting, actually the easiest part, I'll probably need the remaining 5 minutes to explain the algorithm. Boosting just uses lots of decision trees to make better predictions. It's an ensembling algorithm. It builds close to 100, in our case, 100 decision trees. What is important in gradient boosting? That maximum depth of decision trees is restricted to 3. Obviously, both of these are tweakable parameters, but we're gonna go with these values. Why do you need to restrict the depth of the tree? You will soon understand. The first tree in gradient boosting is trained on just Y, just our prices. However, the second tree is trained on the predictions, the values of the Y minus the errors of the first tree. Why do gradient boosting do that? The gradient boosting does that to minimize the error with each iteration. The second tree learns to overcome the error of the previous tree. And by the way, the third tree incorporates the predictions of the first 2 trees. So we keep subtracting prediction of every consecutive tree from our target values to minimize the error and to train to predict the error of the previous trees. So the first tree predicts the price, but the second and all the consecutive ones predict the error. It is achieved through, here's the code, it's pretty simple. When the training is not yet been done and this array is empty, the array of trained trees is empty, the predict method basically outputs zeros. Here's our favorite functions, function zeros, numpy.zeros. It outputs zeros. This block of code hasn't been run in the first iteration because the number of trees is empty. On the first iteration, it's just this. We predict with zeros. To all the trees prediction is 0. That's why on the first iteration, it's just like this. Because the predict method on the first iteration puts zeros. However, on the second one, we've appended a tree to our array of trees, and it iterates over all the trees and records their predictions. Here's the thing called learning rate. For each tree except the first, its values are multiplied by 0.1. It's a life hack to minimize the errors because of the problem called overfitting. However, it's currently beyond the scope of this talk. So I hope it's pretty clear when it comes to gradient boosting. And as you can see, we've declined. Our error, our mean squared error, has significantly declined from 18 to 8.81, and it looks like this. You see that our model fits to data nearly perfect. And to top it up, we've just beaten the sklearn library. So we the error from our gradient boosting implementation is 8.89, and from sklearn 8.95. I remind you that the less the error, the better. So we've just learned how to beat the industry-grade solution sklearn. We've implemented gradient boosting from scratch. We've not compromised and even implemented the decision tree ourselves. We've probably rediscovered the principles behind the decision tree that we can predict with mean, and the more splits, the better. One split predicts like this. Sorry, no split predicts like this. One split predicts like this. And here's a better split. And here's a lot of splits. And here's lots of trees, which makes our predictions even better. So probably that's all for now. Do you have any questions? So I see questions in the chat. Hello, Namrata. Would you kindly share this notebook to follow along? Of course, I will share it right here in the comments section. Feel free to use it for understanding of the gradient boosting, for playing along with this code. You can copy the code. I grant you reading access. It lets you copy the code. Namrata, thank you for the wonderful session. It's very helpful. Thank you for the feedback. I hope it was helpful. If you've got any further question, probably Codementor have some way to contact the speaker, and everyone who is interested to play with this code, please feel free to copy using the link. So the second question, will we get a link to the recording? To be honest, I don't know. However, I hope that Codementor stores all the recordings, and you can access it later. Right now, I can see the recording memo. The interface tells me that the lecture has been recorded. So probably it will be somewhere. I hope that Codementor will let you know how to access it. So I can see that I addressed all the questions. I hope it was interesting and helpful. Good luck on your machine learning journey in applying this algorithm. I tried to be brief. Thank you for the applauding emoji. So it's all for now. Thank you for your attention and good luck.